Honorable session chairs, audience, co-authors, fellow researchers, and organizers of the prestigious STEP 2K25 conference, a very good afternoon to all of you. I am Dr. VSKV Harish, Assistant Professor working in the Department of Electrical Engineering, Netaji Subhas University of Technology, NSUT Delhi. It's a state government university. I shall be presenting on the topic of optimization of proportional integral, that is PI, and fractional order proportional integral, that is FOPI parameters using Gray-Wolf optimization algorithm for improved proton exchange membrane fuel cell, that is PEM fuel cell performance in DC-DC converters, primarily authored by Shri Avijit Raut from Jadavpur University. We have been motivated to work on this topic because the PEM fuel cells are particularly notable due to their high efficiency, very compact design, and a low environmental impact, making them suitable for various applications such as electric vehicles, backup power, and portable devices. However, there are challenges such as unregulated voltage, which is the main attempt from our side to fill the gap, poor performance, and high fuel consumption, which have hindered their widespread commercialization. Our current study is an attempt to fill this gap by developing an advanced control strategy utilizing the Gray-Wolf optimization (GWO) optimization algorithm to optimize FOPI controllers, enhancing the performance of DC-DC converters used with PEMFCs, and we have modeled our structure using MATLAB Simulink. The efficacy of this GWO based FOPI controller has been compared with much more used controllers in optimal controllers, which have been published in research works, which are majorly the genetic algorithm based PI controllers and the PSO based PI controllers. We have used certain matrices or indices for performance comparison in terms of integral absolute error, integral squared error, and integral time absolute error, which becomes our optimization objective function. And we have used equal weights, and we have seen the results in terms of transient response, stability, and energy efficiency or the energy performance. If we talk about the literature survey, detailed literature survey is there in the paper. Several papers have been published on FOPI tuning, basically using genetic algorithm and particle swarm optimization. Firstly, PSO-based FOPIs, as you can see, uses swarm intelligence to optimize the parameters by mimicking the social behavior of a swarm of birds. Of course, it offers faster convergence, moderate parameter sensitivity, and is simpler to implement. But the robustness and escaping the local minima while being flexible is still an issue. On the other hand, if we look towards the genetic algorithm based optimization of FOPI controller, it employs evolutionary selection, crossover, and mutation to optimize the parameters, while it provides thorough exploration of all the solution space. There is a slower convergence as compared to PSO. That's what we have used. That's what the literature says. GA is also highly sensitive to the uncertainty in the parameters and pretty high complexity due to multiple computational stages. So we are tried to attack on the limitations and address, not attack, sorry, but address the limitations of genetic algorithm and PSO based optimization by using GWO, which is the Gray-Wolf optimization. Just a brief introduction about what is GWO. Gray-Wolf optimization is a nature-inspired meta-heuristic algorithm which was developed around 2014 that models the social hierarchy and hunting strategies of gray wolves in the wild. It is again a population-based optimization technique that mimics the cooperative behavior of the wolves during their hunting exercise. The GWO algorithm classifies the search agents into four hierarchical groups: alpha, which becomes the best solution; beta, which becomes the second best solution; delta, which becomes the third best solution; and omega, which becomes the remaining solutions. These groups collaborate to encircle, chase the prey and capture the prey, leading to optimal solutions in the search space. GW in general has gained popularity due to its simplicity, adaptability, efficiency, making it a powerful tool for solving various optimization problems. And the context of our current work of fractional order PI tuning, that's why we have used the GWO, because the rules follow the shortest path to converge towards the best possible parameters, ensuring better performance or enhanced performance. We understand that a stack of fuel cell cannot be directly connected to the load. We require a power electronic interface. Here we have used a simple but a basic DC-DC boost converter, whose operation, that is the gate signal, is being controlled using the fractional order PI controller. What we have done is we have used this controller because there will not be a constant load, there will be load fluctuations, and we want to have a converter or a control in such a way that the supply and demand is followed in such a way that the voltage control is happening. There is a balance, and this balance is being achieved, we are achieving this balance by taking into consideration that the steady state error is also being minimized. The slide which you are seeing on your screen presents the system parameters which have been used in our PMFFCs. Majorly we have taken from our IEEE transaction paper. The key parameters include the operating temperature of 353 Kelvin, which is the standard test conditions, a cell current density of 100 ampere per meter square, and a number of total cells totaling to 35. The system's reactant factors for oxygen, hydrogen, and nitrogen have also been listed here along with their inlet flow rates, and these parameters play a very crucial role in determining the fuel cells, the supply side performance, efficiency, and stability. As you can see here, we have also given a snapshot only for in this PPT, not in the paper, to get a MATLAB Simulink snapshot, which we have used in our paper. It is very simple model, and we have used the MATLAB version of 2022. We have used the inbuilt library PM fuel cell stack. If you double click it and see, we can have different types of fuel cells. We have used PM fuel cells, which is connected to a DC load represented by a constant impedance load and ideal resistance. This is one of the fewest limitations of our work. In future, we have already started to work on a journal paper where we are trying to regulate a converter, bidirectional converter, connect a battery also, and regulate a BLDC motor. Now, if we see the simulation results, as we can see from the simulation results for a DC-DC boost converter controlled using two different approaches. One is the PI controller and one is the fractional order PI controller. In the first set of plots, we can see, we observe that the voltage, current, and power output for the converter using a PI controller, while the system stabilizes, there is a noticeable overshoot and a longer settling time leading to transient fluctuations. In contrast, the second set of plots where we have used the fractional order PI controller, we can see an improved stability, a faster settling time, and a reduced overshoot. So the FOPI's controller's ability to handle non-linearities and dynamic variations have resulted in smoother and efficient system performance. We also conducted a comparative analysis for the terminal voltage and the current response under variable load conditions for two control strategies, the PI and the PSO based FOPI. In the first set of plots again, we can see an observable significant voltage drop and a slow current stabilization during the load changes. Also, there is a noticeable overshoot and a longer settling time indicating inefficiencies in the transient response. Whereas in the case of FOPI optimization or FOPI controller, we can see we are getting better stable voltage, reduced overshoot, and a very faster current convergence. The improved control response minimizes the fluctuations, making it more efficient in handling the dynamic load variations. If we see the comparison of voltage and current responses under load variations from the load side, we can see that the first set of plots where we have used only GAPI, there is still a noticeable transient spike in the voltage at around very few second here at 10 seconds. In contrast, we obtain a much more stable voltage. There is a spike, but very small magnitude when we use the GWO FOPI controller. So the Grey Wolf Optimizer FOPI controller outperforms the GA controller or the PSO controller, which we saw in the previous slide, in minimizing the transient disturbances, making it a much more better optimizer. Here also we see that all the three methods achieve a similar steady state power output. However, if there is a sudden change in load, which is a step change in around 10 seconds, the GWO optimizer provides smallest deviation, better stability, and minimal overshoot. These are the parameters for FOPI, which the tunable parameters when we tune using the GWOPI, and we can see that we get much better performance in terms of rise time, that is in seconds. I'm extremely sorry that I have not written the index here. Rise time in settling time in seconds, peak overshoot in a percentage, and the peak time in seconds. Now, if we compare the performance metrics of GWFOPI, we can see that the GWFOPI controller achieved a rise time of 0.1358 seconds as compared to 0.3251 second and 0.4832 second for GAPI. And we can see that in other cases as well, for the settling time improvement, for the peak overshoot, for optimization efficiency, and the error minimization also, where we have used the weighted IAE, ITE, and ITSE, and we see that we are getting much better results in terms of GWO FOPI. This is a GWO FOPI results, and the other two are for the GA PSO results. So in conclusion, we can conclude that we started with a basic white box model of a PEMFC using the MATLAB toolbox of SimScape and SimPower systems, and we developed designed a DC-DC boost converter and controlled the converter using the GWFOPI. In the simulation, the benchmark was where along with which we were comparing our GWFOPI was the GA FOPI and the PSO based FOPI, and we have seen that through various results that the GWFOPI showed much better results in terms of transient time, settling time, that is the time domain specifications, and also the steady state error. We are developing two more research papers out of it, where, as I told you, we are using the load as BLDC load and then trying to make and explore other optimization techniques such as TLBO and COVID optimization, and also trying to make the implementation of machine learning based techniques. Thank you very much for your patient listening. Me and Avjit Raut will be attending this session, and we will be happy to take any questions that you have now. So thank you all. Thank you, honorable session chairs. Thank you to the organizers.